Today we are going to take the topic of amplitude modulation. In amplitude modulation, the signal wave that is known as a modulating wave is superimposed on a high frequency wave that is the carrier wave in such a way that the amplitude of the modulated wave is going to change in accordance with the modulating signal, but its frequency remains same as that of the carrier wave. We'll see that in the definition. In amplitude modulation, signal wave that is known as a modulating wave is superimposed on a high frequency wave that is a carrier wave in such a way that frequency of the resultant that is the modulated wave is same as that of the carrier wave, but amplitude varies in accordance with the instantaneous amplitude of modulating signal. So whatever we have learned in the definition, we are going to see its waveform. This is the waveform I am plotting for the modulating or the signal. This is our signal wave known as the modulating wave. Next is the carrier wave. So this is the carrier wave or a high frequency wave. Now these two waves, this is the signal and the carrier wave, these two are going to superimpose. Now this signal wave is superimposed on high frequency carrier wave in such a way that the high frequency will have the amplitude as that of the signal wave, but its frequency remains the same. Now the resultant superimposed waveform will be like this. The frequency remains same and the amplitude varies according to the signal wave. For the positive half cycle, the high frequency amplitude increases, and for the negative half cycle, the amplitude decreases according to the signal wave. These are the wave envelopes. So this is our modulated or the resultant wave. This modulated wave is amplitude modulated wave. This is your amplitude modulated wave. So whatever we have learned from the definition, we have seen the waveforms of the amplitude modulation in which we are having this type of waveform. Now we are going to derive the mathematical expression for the amplitude modulated wave. For that, let EC is the instantaneous voltage of carrier wave and EM is the instantaneous voltage of signal wave or the modulating wave. So the expression for these waves will be, for the carrier wave it will be EC, mark it as equation number 1, and waveform for the modulating wave is Now, here EC and EM, these are the amplitudes of this carrier wave, and this is for the modulating wave. And omega C and omega M, these are the angular frequencies of these respective waves, where EC and EM are amplitudes and omega C and omega M are angular frequencies of carrier wave and modulating wave respectively. Now, the resultant modulated wave, by superimposing these two waves according to the amplitude modulation, will be such that the angular frequency of the carrier wave remains omega c in the resultant wave. Only the amplitude of this wave will be varying according to the modulating wave. That is how we can write down, let E is the resultant wave, then this waveform is written like this. Mark it as equation number 3. Here, A is the amplitude of the resultant modulated wave, and frequency as per the definition remains omega c, where A is the amplitude of the modulated wave. This is equal to, now putting the value of the amplitude of modulated wave in its equation, we will get now. Here we will introduce one more factor known as modulation index or modulation factor or amplitude modulating factor. This is equal to ratio of the amplitudes of modulating signal to the carrier wave. From here we get EM is equal to ME EC. Now, putting this value in the above equation, we have E equal to EC sine omega CT plus now we'll be using trigonometry to solve this expression using trigonometry relation, that is 2 sine A sine B. It is equal to cos A minus B minus cos A plus B. So the above equation is written as we have multiplied and divided by 2. Using the relation, this thing can be written as this is the final expression for the amplitude modulated wave. This equation consists of three waveforms. The amplitude of the first waveform is EC and the frequency, say nu, C is given by 2 pi. How I have written this? We know about one relation. Angular frequency is equal to 2 pi nu, the frequency. From here we get frequency is equal to nu up equal to 2 pi upon angular frequency. So we get this relation. Now this is our modified waveform. This is also the modified one. Now for this waveform, the amplitude is MA EC by 2. Nu C minus nu M. And for this also, we are having amplitude the same MEC by 2 and the frequency will be given by this is our lower side frequency. And this is the upper side band frequency. Now, knowing about the amplitude and the frequency of amplitude modulated wave, we can plot the frequency spectrum of amplitude modulated wave. This side will plot amplitude and here we are having the frequency. One of our amplitude is ME EC by 2 and the other one is EC. Suppose here our LSB nu C minus nu M is lying. So this is our LSB line, this is our frequency of the carrier wave and this is our upper side band is lying. The signal is contained only in these side bands and this frequency nu C of the carrier wave is filtered out before the receiving antenna. So these are the important conclusion. The signal is contained in sidebands only. Carrier wave is filtered out before receiving antenna. Now we are going to calculate the bandwidth of amplitude modulated signal. The amplitude modulated signal AM is lying between the frequency Fc plus Fm. This is the upper side band frequency, and Fc minus Fm. This is the lower side band frequency. The signal is contained within these frequencies, and for bandwidth, the formula is upper frequency minus lower frequency. So we'll subtract Fc plus Fm and we get so bandwidth comes out to be equal to twice of frequency of the modulating signal. Hence we conclude bandwidth of amplitude modulating wave is twice the frequency of modulating signal. Now we are taking our next topic, that is amplitude modulating factor or modulation index. Already we have taken this factor in our derivation. It is denoted by MA. This is our modulation index. Considering the maximum and minimum amplitude of modulated wave, we have E maximum is equal to EC plus EM, and E minimum is EC minus EM. Mark it as equation number 1 and 2. On solving these two equations, we get EC is equal to E maximum plus E minimum by 2, and EM comes out to be E maximum minus E minimum by 2. So our modulation index ME, that is the ratio of modulating amplitude to the amplitude of the carrier wave, is given by E maximum minus E minimum to E maximum plus E minimum. So what is this actually, this modulation index is? Now we are going to talk about the physical significance of modulation index, that is MA. Basically, it finds out the extent up to which the amplitude of the carrier wave is being changed by the modulating signal. MA tells about the extent up to which the amplitude of carrier wave is changed by modulating signal. What does it mean? It means it tells the quality of received signal waves, because more efficient the changing of the carrier wave with respect to the amplitude of the modulating signal, better will be the quality. Now, usually this MA is less than 1. If MA is having small value, what does it mean? It means the amplitude modification of carrier wave is not efficient. If MA is having small value, then the modulated signal wave at reception is not clear. It is weak. On the other hand, if MA is having greater value, what does it mean? This modulation is being done efficiently, and at the output we are having the clear and the strength of the output is good. So if MA is having greater value, the transmitted signal will be clear and having good strength. In some cases, if MA is greater than 1, it means there is not the proper modulation. Rather, there is over modulation of the carrier wave, and hence at the reception, that signal wave won't be received clear. If MA is greater than 1, there is over modulation of carrier wave, and at the reception of transmitted wave, signal wave is distorted. So this is all about the modulation index factor.